Okay, I want to tell you about harmonic motion. This is the first video of probably several on harmonic motion. To do this, we're going to use what we know about circular motion to study harmonic motion. So here is an object that is going to be moving around in a circle at a certain amount of radians per second. It'll be going around. Yeah, let me dim these lights a little bit. And so this is going to be going around in a circle with a constant omega, a constant angular velocity. And this is attached to a spring. Now the spring is stretched out right now. In its relaxed position, the object would be like right here if the spring were relaxed. When the spring is relaxed, the position that the object is in when the spring is relaxed is going to be called equilibrium. That's the equilibrium position. When I hit run, this thing is going to get pulled this way because the spring's pulling it. And when it hits the equilibrium position, even though it doesn't have any force on it at that point, it will have gained some velocity. So its momentum is going to carry it forward. And so it will start to compress the spring. It will start crunching the spring, which means the spring will push the other way back. And so it will come to here, and it's going to just oscillate back and forth on this spring, going back and forth. We call that motion simple harmonic motion. And I've set this up so that the circular motion is in sync with the harmonic motion. So here goes. Well, let's run it. So notice that whenever the circle is right here, the box is right there. And when the circle is right here, the box is right here. In fact, if we had light, can you imagine light coming down like this, the direction, light beams coming down the direction my fingers are pointing? And if that circle were a little raised off the disk, can you imagine that there'd be a shadow on the ground? There'd be a shadow of that red circle, and it would be going like this. The shadow would be going like this. It'd be in sync with the harmonic motion on the bottom. So the shadow of that circle is just the x component of the circular motion. I'll say that again. The shadow of that circle is the x component of that circular motion. And it turns out that the shadow would have the same period as the box. And that would have the same period as the ball. Okay, so let's turn this off. Let's turn the lights up a little bit. And let's take a look at this system. I'm going to have to adjust this a little bit. Move this up a little bit like that. Perfect. Perfect. Okay. So get out of that shadow. Okay, so here is this is the system I just showed you. It's got no friction. The point where the spring is unstretched right now, that's x equals 0. And it's oscillating between its two endpoints. The furthest point out we're going to call A. A is for amplitude. And that's as far out as it will go. And then it will shoot back and shoot to negative A. And we'll say the mass of the box is m, the spring constant is k. Okay. Well, as I said before, we're going to use the circle to study the harmonic motion, the simple harmonic motion. And so by the time this thing is right here, it will, when it's right here, it's casting a shadow there. That's the shadow of this thing. Light rays are coming down like this. And the shadow of this thing, this is raised off the disk a little bit. And so the shadow of this thing is right there. But when this is here, the shadow is no longer here. The shadow is straight down. Okay. Now, do you recognize that the radius of the circle and how far out the shadow will be, A, they are equal to one another? So A is equal to R. And this distance, x, right here, where it will be, that x distance, where it will be when this is here, is just if I draw this and call this theta, that's an angle theta, then, and if this is r or a, I'm not going to call this r anymore, I'm going to call it a, then this is going to be, this distance right here is the same as x, our x distance. So this distance is a times the cosine of theta. That's what this distance is, and that's what that distance is. Okay, now, a couple things. If this is spinning with an omega, let's say that's spinning with an omega, and it's a constant angular velocity, then let's say that, do you remember how angular velocity, omega, is delta theta over delta t? But delta theta is theta final minus theta initial over t final minus t initial. And we're going to start our watch. T initial will be at 0 seconds. So this is going to be 0 seconds. And we're going to start it right there. So theta will be 0. So both of these are 0. Boom, boom. So it looks like, I'm going to call theta final just theta then. So theta over time, that's omega. So that means that theta is equal to omega t. Okay, you want to know how big theta is? Well, we have a certain constant omega and let it run for a time t, and you'll be at different places around the circle. So x, how far you are from the equilibrium, this is the equilibrium position. I'll call it EQ for equilibrium. Then, let me get this away from the shadow. Perfect, perfect. Okay. So I'm going to say that x then is how far the shadow is from equilibrium. There's the shadow, the new shadow. It's going to be equal to a times the cosine of theta. But theta is omega t, so x equals a cosine omega t. Okay, well, if that's the displacement, the position at any given time, put it any time you want, and that will tell you where it's going to be along here. It's going to bounce back and forth between these two spots. Well, that's the position at any time t. Then the velocity is just the derivative of this. Now, the derivative of a cosine function is a sine function, but you got a chain rule going on in here too. So what you get is a omega sine omega t. I'll explain how this works in class if you don't follow what I'm saying, and that's a negative sign there. So the derivative of x with respect to time, that's what this is. The derivative of x with respect to time is going to be a omega sine omega t. And now if I want the acceleration, that would be the derivative of v with respect to t. And so the acceleration of that shadow, if I take one more derivative, it looks like I'm going to get negative a omega squared times the cosine of omega t. That's just the second derivative of the position vector. Okay, so those are our three functions for kinematics. Where we know now where the position of the thing is, where the velocity is, and where the acceleration, what it is, how it varies with time. I want to point out one other thing. The maximum position that you'll ever be from the equilibrium is A. Now that makes sense because isn't cosine of any angle, isn't it going to oscillate between 1 and negative 1? So you see that? This is always going to go between 1 and negative 1. So the biggest x can be is when this is 1 times A. So the biggest x can be, x max will be equal to A. What will be Vmax? What will be the biggest Vmax can ever be? That would be A omega.